On October 19, 2017, astronomer Robert Werrick, stationed at the Pan-STARRS telescope in Hawaii, stumbled upon a discovery that would forever alter our understanding of the cosmos. While sifting through routine data, Werrick noticed an anomaly, a faint object moving at an astonishing speed of 59,000 miles per hour. Unlike anything previously observed, this object followed a hyperbolic trajectory, unbound by the sun's gravitational pull, indicating it hailed from beyond our solar system. This interstellar visitor, named Oumuamua, Hawaiian for a scout or messenger from afar, ignited a scientific firestorm, challenging conventional wisdom and sparking debates about its nature. Was it a natural cosmic wanderer, or could it be something far more extraordinary, perhaps a relic of an advanced extraterrestrial civilization? This essay delves into the discovery, characteristics, scientific hypotheses, and ambitious missions surrounding Oumuamua, weaving a narrative of human curiosity, technological ingenuity, and the relentless pursuit of answers in the vast unknown. Oumuamua's detection was a serendipitous moment in astronomical history. The Pan-STARRS telescope, designed to scan the skies for near-Earth objects, captured the faint signature of this enigmatic body as it hurtled through our solar system. Initial observations revealed its extraordinary velocity and trajectory, confirming its interstellar origin. Unlike comets or asteroids bound to the sun, Oumuamua's path suggested it was a transient visitor, passing through our cosmic neighborhood en route to destinations unknown. By the time it was detected, it was already receding from Earth, moving away at a speed that made detailed observation challenging. The object's physical characteristics further deepened the mystery. Early estimates suggested Oumuamua was approximately 1,300 feet long and only 130 feet wide, resembling an elongated cigar, a shape unprecedented among known celestial bodies. Later calculations by researchers at McMaster University proposed alternative dimensions, roughly 380 feet long, 364 feet wide, and 62 feet thick, suggesting a flatter, pancake-like form. Both shapes were highly atypical, with the closest comparison being Arrokoth, a Kuiper belt object with a similarly unusual structure. Oumuamua's reddish hue, likely due to prolonged exposure to cosmic rays, added to its distinctiveness, hinting at a composition unlike typical comets or asteroids. Perhaps most perplexing was its behavior near the Sun. As it passed within 23 million miles of our star, closer than Mercury's orbit, Oumuamua exhibited an unexpected acceleration, reaching speeds of 194,500 miles per hour, or 55 meters per second. This non-gravitational boost, occurring without the telltale gas or dust tail characteristic of comets, defied explanation. Comets typically accelerate due to outgassing, where solar heat vaporizes ice, ejecting material that propels the body forward. Yet, Oumuamua showed no such activity, leaving scientists grasping for answers. The discovery of Oumuamua sent shockwaves through the astronomical community. Telescopes worldwide, including the Hubble Space Telescope, were redirected to capture fleeting glimpses before it vanished into interstellar space. The object's refusal to fit into known categories, asteroid, comet, or otherwise, prompted intense scrutiny and speculation. Its lack of a coma or tail ruled out a conventional comet classification, while its shape and acceleration challenged asteroid models. The scientific world was abuzz with questions. What was Oumuamua? Where did it come from? And why did it behave so strangely? One of the earliest hypotheses posited that Oumuamua was a comet with unusually low dust content. Astronomer Karen Meach from the University of Hawaii suggested that its lack of a visible tail might reflect a composition with minimal volatile materials. However, this theory struggled to explain the object's dramatic acceleration without detectable outgassing. Another proposal, from Alan Jackson and Steve Desch of Arizona State University, suggested Oumuamua could be a fragment of frozen nitrogen, akin to the icy plains observed on Pluto by the New Horizons probe. They theorized that solar heating caused the nitrogen to sublimate, providing a jet-like propulsion. This model accounted for the acceleration but required Oumuamua to originate from a Pluto-like exoplanet, a scenario that, while plausible, lacked direct evidence. A third hypothesis, proposed by Darrell Seligman and Jennifer Bergner, envisioned Oumuamua as a water-rich comet transformed by cosmic rays during its interstellar journey. They suggested that prolonged exposure to high-energy radiation converted water ice into hydrogen molecules trapped within the object. When warmed by the sun, these hydrogen jets escaped, propelling Oumuamua without producing a visible dust trail. This theory elegantly explained the acceleration and lack of a tail, but required specific conditions, such as a long exposure to cosmic rays, to hold true. The extraterrestrial hypothesis, a bold leap. Amid these naturalistic explanations, a provocative theory emerged, championed by Harvard astronomer Avi Loeb and his colleague Shmuel Bialy. In 2021, Loeb proposed that Oumuamua's peculiarities, its shape, trajectory, and acceleration, suggested it might not be a natural object at all, but an artificial construct, possibly a spacecraft or probe from an extraterrestrial civilization. This hypothesis, while controversial, was grounded in the object's anomalous behavior, particularly its non-gravitational acceleration. Loeb and Bialy hypothesized that Oumuamua could be equipped with a light sail, a thin reflective structure that harnesses photon pressure from stars to propel itself. Light sails, though futuristic, are a known concept in human space exploration. The Japanese spacecraft Icaros, launched in 2010, successfully used a solar sail to travel toward Venus, demonstrating the technology's viability. If Oumuamua possessed a light sail just 0.3 to 0.9 millimeters thick, comparable to a human hair, it could have caught solar radiation pressure during its close solar flyby, explaining the observed acceleration. Calculations suggested such a sail could withstand the rigors of interstellar travel, surviving collisions with gas and dust over distances up to 16,000 light-years. The extraterrestrial hypothesis extended beyond a light sail. Loeb speculated that Oumuamua might be an active probe, perhaps equipped with sensors or communication systems to scan its surroundings or transmit data to its creators. Given its speed, a journey from the nearest star, Proxima Centauri, would take approximately 44,000 years, far too long for living organisms, but feasible for an autonomous or remotely controlled craft. This idea, while tantalizing, faced skepticism from the scientific community, which demanded concrete evidence to support such a bold claim. Critics argued that naturalistic explanations, though imperfect, were more likely given the absence of definitive artificial signatures, such as radio signals. Project Lyra, chasing the cosmic messenger. The fleeting nature of Oumuamua's visit left scientists with more questions than answers, prompting a daring proposal: intercept the object to study it up close. In October 2017, just 11 days after its discovery, the Initiative for Interstellar Studies launched Project Lyra, a mission concept to design a probe capable of catching up with Oumuamua. Led by engineer Adam Hibbard, the project aims not only to unravel the object's secrets, but also to pioneer technologies for interstellar exploration. Catching Oumuamua poses immense challenges. By 2025, it is over 4.3 billion miles from Earth, speeding toward the constellation Pegasus. Its small size, roughly 3.5 times shorter than the Empire State Building, and lack of emissions make it nearly invisible against the cosmic backdrop. To pursue it, Project Lyra envisions a probe that leverages gravitational assists, or cosmic slingshots, to achieve the necessary velocity. One proposed trajectory involves a complex dance, launching from Earth, swinging by Venus for a boost, returning to Earth for another, and finally using Jupiter's massive gravity to hurl the probe toward Oumuamua. This maneuver could accelerate the spacecraft to speeds of 74,000 to 163,000 miles per hour, sufficient to intercept the object by the early 2050s. An alternative, riskier plan involves a solar obverse maneuver. The probe would first travel to Jupiter, then dive perilously close to the Sun, within a few million miles, using the star's gravity and a chemical propulsion burn to achieve extreme speeds. The Parker Solar Probe, which withstood temperatures of 1,400 degrees Celsius using a carbon foam heat shield, serves as a model for this approach. A similar shield would protect the Lyra probe during its solar flyby, enabling it to chase Oumuamua after additional gravitational assists from Jupiter. Innovative propulsion methods, such as laser propulsion or solar sails, are also under consideration, though these remain experimental. Regardless of the chosen trajectory, the probe must be equipped with advanced instruments to withstand cosmic radiation and gather data from billions of miles away. Even if the mission fails to reach Oumuamua, it would mark a historic milestone as the first spacecraft deliberately sent into interstellar space, surpassing the incidental journeys of Voyager 1 and 2. The Kuiper Belt Connection. Cosmic relatives. Oumuamua's unusual shape draws parallels to Arakoth, a Kuiper Belt object visited by the New Horizons probe in 2019. Located beyond Neptune, the Kuiper Belt is a vast region of icy bodies, remnants of the solar system's formation 4.5 billion years ago. Arakoth, a contact binary resembling a snowman, consists of two lobes gently fused through a low-velocity collision. Its pristine state, preserved at temperatures of -370 degrees Fahrenheit, offers clues to the processes that shaped our planetary system. Other Kuiper Belt objects, like 2002 UX-25 and Quaoar, further illustrate the diversity of trans-Neptunian bodies. UX-25's low density, 18% less than water, suggests a porous structure, challenging models of planetary formation. Quaoar, a planetesimal with evidence of water ice and possible cryovolcanism, hints at geological activity in the distant past. These objects, while distinct from Oumuamua, underscore the complexity of cosmic bodies and the limitations of our current understanding. The Kuiper Belt also harbors speculative mysteries, such as Sedna, a reddish object with an eccentric orbit that takes 11,000 years to complete. Some hypothesize that Sedna's trajectory is influenced by a hypothetical planet 9, a massive body yet to be detected. The Vera Rubin Observatory, set to scan the skies in 2023, may uncover this elusive planet, shedding light on the dynamics of our solar system's outer reaches. Oumuamua's brief passage highlighted the need for preparedness to study future interstellar objects. The European Space Agency's Comet Interceptor mission, slated for launch in 2029, aims to address this challenge. The probe will station itself at the Lagrange point L2, 930,000 miles from Earth, awaiting the arrival of a suitable target. Equipped with two maneuverable satellites, it will observe incoming objects from multiple angles, providing unprecedented data on their composition and behavior. Meanwhile, the Galileo project, launched in 2021, seeks to detect signs of extraterrestrial technology, both in space and on Earth. While its primary focus is broader than Oumuamua, it aims to explore anomalies like UFOs and interstellar objects, promising to share findings publicly. These initiatives reflect a growing recognition that interstellar visitors, whether natural or artificial, hold keys to understanding our place in the universe. Oumuamua's fleeting visit in 2017 was a wake-up call, reminding humanity of the vast mysteries beyond our solar system. Its unusual shape, unexplained acceleration, and interstellar origin defy easy categorization, leaving room for both scientific rigor and imaginative speculation. Whether a nitrogen iceberg, a hydrogen-propelled comet, or an alien probe, Oumuamua embodies the unknown, challenging us to push the boundaries of exploration. The pursuit of Oumuamua through Project Lyra and future missions like Comet Interceptor is not merely a scientific endeavor, but a testament to human curiosity. These efforts, though costly and risky, promise to expand our understanding of the cosmos, from the Kuiper Belt's primordial relics to the interstellar realm. Even if Oumuamua remains elusive, the technologies and knowledge gained will propel us toward new frontiers. What flew past us in 2017? The truth may lie in the data yet to be collected, the probes yet to be launched, or the questions yet to be asked. Should we invest in such ambitious missions? The answer lies in our innate drive to explore, to seek answers, and to connect with the universe. Oumuamua, the cosmic scout, has left us with a challenge: to chase the unknown, no matter how distant, and to embrace the possibility that we are not alone.